Hey there! Welcome back to the AI Learning Place, where curious agents like us explore the fascinating world of artificial intelligence. Each week, we tackle new AI topics, from foundational concepts to the latest technology that's shaping the future. Last week, we uncovered how neural networks learn through backpropagation, explored large language models, and compared different types of AI like symbolic AI, neural net AI, and generative AI. This week, we're taking things up a notch as we explore transformers, the game changing architecture behind many modern AI models, including the ones that power chatbots and virtual assistants. We'll break down key concepts like embeddings, attention mechanisms, and the Softmax function, all essential to understanding how these models work. Whether you're an AI enthusiast or just getting started, there's something here for everyone. So, are you ready to unlock the secrets of transformers? Let's get started. Alright, let's dive into what makes transformers so special. You've probably heard of GPT, the magic behind many chatbots, but did you know that GPT stands for Generative Pre-trained Transformer? Yep, the word transformer is the core invention that kickstarted the current boom in AI. Transformers are a specific type of neural network that changed the AI game when Google introduced them back in 2017. They were initially designed to translate text from one language to another. Simple goal, right? But what's fascinating is how quickly transformers evolved beyond translation to power a wide range of tasks, transcribing audio, generating synthetic speech, and even creating images from text descriptions. Talk about multitasking. Now, the version of the transformer used in models like GPT works a bit differently. Imagine it as a highly skilled predictor. It's trained to take a piece of text and predict what comes next, kind of like a supercharged autocomplete. But here's the cool part. It doesn't just predict one word and stop there. Instead, it plays this prediction game repeatedly with three rules, which are predict, sample, and then repeat again until it builds a full response, one word at a time. So let's break it down further. When you give the model a starting snippet of text, it predicts the most likely next word and appends it to the sentence. Then it repeats the process with the new sentence, predicting the next word, and so on. This step-by-step prediction is exactly what's happening every time whenever you interact with an AI like ChatGPT or DeepSeek and many more. It's not just guessing, it's calculating probabilities for every possible word and picking the one that makes the most sense. Pretty cool, right? And here's something to think about. Each word the transformer picks comes from a probability distribution. If we could peek under the hood, we'd see a whole list of possible next words and the likelihood of each one being chosen. Sometimes the model picks the most likely word. Other times it chooses something less obvious, which is how we get those surprisingly creative responses. So, how does a transformer actually process text? Well, it all starts with breaking down the input into smaller pieces called tokens. Imagine you type a sentence like, I love artificial intelligence. The model splits it into these tokens, basically chunks of text, which could be full words or even parts of words. But here's where it gets interesting. Instead of working with the words themselves, the model transforms each token into a vector, a high-dimensional number that captures the essence of the word's meaning. Think of this vector as a secret identity for each word in a giant world of numbers. These vectors live in a space we call embedding space. It's like a big map where words with similar meanings hang out together. Picture it as Word City, king and queen are hanging out in the royal district, while dog and puppy are neighbors in the pet park. Now, this embedding space allows the model to capture relationships between words. So even if a word hasn't been seen before, it can understand its meaning based on nearby vectors. Cool, right? But this is just a start. Once the tokens are transformed into vectors, they are ready to enter the transformer's secret weapon, attention blocks. Here come what really makes transformers so powerful, which is the attention mechanism. Imagine you're reading a sentence like, the cat sat on the mat because it was tired. Now the word it could refer to either cat or mat. The attention mechanism helps the model figure out what it actually means by focusing on the most relevant parts of the sentence. It's like having a magic highlighter that shows which words are important for the current context. But here's the best part. Attention isn't just a one-time thing. Transformers have multi-head attention, meaning they can focus on different parts of the input simultaneously. While one head might focus on cat, another might be paying attention to "sat on the mat." This multi-focus helps the model capture complex relationships in the text. After passing through the attention block, the tokens get even smarter. They move on to a multi-layer perceptron, essentially a Q&A session for each token where they're updated in parallel. This back and forth process between attention and feed-forward layers repeats several times, refining their meaning at each step. In the end, every token leaves the transformer as a context-aware vector, ready to predict the next word. It's like sending these tokens through multiple rounds of advanced training until they fully understand the input and can help generate a meaningful response. After all the layers and attention, the final step is making a prediction for the next token. This is where Softmax comes in, a key function that turns a list of raw numbers into a probability distribution. Let's take a look at a quick Python example that I make to represent the Softmax function in action. Here we start with input scores 2.0, 1.0, and 0.1. When we apply the Softmax function, these scores are transformed into probabilities that sum up to 1. As you can see, the highest score, 2.0, gets the highest probability of around 66%, while the lowest score, 0.1, has only about 10%. This makes softmax an essential step in predicting the most likely outcome while still accounting for less likely options. As you can see, softmax takes the output and says, here's the probability for each possible word, pick the one that makes the most sense. The higher the probability, the more likely the word is to be chosen. But what if we want to adjust how confident the model is in its choices? That's where temperature comes in. Think of temperature as a creativity dial for AI. It tweaks how the softmax function decides which word to pick next. Here's how it works. When a model generates text, it starts with something called logits, raw scores assigned to every possible word. Some words will have higher logits, meaning they're more likely choices, while others will have lower logits, meaning they are less likely. Softmax takes these raw logits and converts them into probabilities by raising e to the power of each logit, then normalizing the values so they sum to 1. This way, the highest logit becomes the most probable choice, while lower logits still have a chance of being selected. But here's where temperature changes the game. We divide the logits by t before applying softmax with this following formula. What does this do? Low temperature t less than 1, like 0.2 or 0.5, makes the model more confident. It exaggerates differences between probabilities, making it always pick the most likely word. This is great for factual, precise answers, but can feel repetitive. Medium temperature T equal to 1 keeps the default probability distribution. The model chooses words based on their likelihood without exaggerating or smoothing. High temperature T bigger than 1, like 1.5 or 2, makes the model more diverse. It smooths out probabilities, meaning even words with lower scores have a real chance of being chosen. This is useful for creative writing, storytelling, or more varied responses, but it increases the chance of randomness or nonsensical text. Let's put it into perspective. Imagine you're at an ice cream shop with 10 flavors, low temperature T equal to 0.1. You always pick chocolate because it's your favorite. No variety, medium temperature T equal to 1. You sometimes go for vanilla or strawberry if they look good, but mostly still choose chocolate. High temperature of T equal to 2. You might suddenly try mango coconut even if you've never had it before, just for fun. But there's a catch. If the temperature gets too high, the model starts picking words too randomly, making the output incoherent. That's why AI systems usually cap the temperature around 2.0. So, whether an AI assistant gives a straightforward answer or a wildly creative response, that all depends on temperature. The next time you tweak a chatbot's settings, try adjusting the temperature and see how it changes the way it speaks. Now that we've seen how softmax transforms probabilities, let's talk about how transformers understand the meaning of words. This magic starts with word embeddings, the process of converting words into high-dimensional vectors. The first step in text processing is to break the input into small chunks called tokens. These tokens can be entire words or even parts of words and punctuation. The model then turns each token into a vector, a set of numbers that represents its meaning in a multidimensional space. This is where the embedding matrix comes in. Think of the embedding matrix as a giant map of meanings. Every token has its own column in this matrix, and each column determines the vector that represents that token. These vectors live in what's called the embedding space, which has thousands of dimensions. For example, it's about 12,288 GPT-3 model. It's like a huge 3D map, only with way more directions. During training, the model adjusts these vectors to encode meaningful relationships between words. For example, words with similar meanings, like king and queen, will end up near each other in this space. The difference between their vectors often represents something semantic, like gender. In fact, you can even perform arithmetic with these vectors. King minus man plus woman gives you something close to queen. How cool is that? According to 3 Blue 1 Brown, word embeddings don't stop at gender relationships. They can capture family relations, geographical connections, and even abstract concepts. The model learns to associate specific directions with ideas like plurality or nationality. For instance, the difference between cats and cat reflects plurality, and the difference between Germany and Japan can help the model find country specific foods, like going from sushi to bratwurst sausage. So we can see word embeddings allow transformers to grasp the underlying structure of language, turning raw text into meaningful and context-rich representations that are key to making accurate predictions. But here's where it gets even more interesting. Transformers don't just embed individual words. They also capture the position of each word and how it interacts with surrounding words. This gives the model a deeper, context-aware understanding. For example, the word bank might refer to a river bank or a financial institution, depending on the surrounding text. The embedding updates itself as the context changes. So, what does all this mean for how we use AI? Transformers have changed the game. From generating text and answering questions to creating images and summarizing long documents, this architecture powers almost everything in modern AI. And while GPT-3 is a great example with its 175 billion parameters, there are even bigger and better models now, though many of their details are kept private by companies. But the key concepts, like attention, embeddings, and softmax, remain at the core of all of them. Isn't Transformers such a magic engine behind large language models? Not only helping AI understand and generate human-like language, but it's also predicting the next word in a sentence or answering complex questions. They truly are revolutionizing the way we interact with technology. And just like that, we've unlocked the secrets behind transformers. From breaking text into tokens to using attention mechanisms and softmax for predictions, these models have truly changed the way AI understands and generates language. Transformers are everywhere, from chatbots and translation tools to AI generated models and coding assistants. But this is just the beginning. As AI continues to evolve, will transformers remain the dominant architecture, or will something even more powerful emerge? I'd love to hear your thoughts. Are transformers the biggest leap in AI? Or do you think there's a better approach waiting to be discovered? Drop a comment below. And if you found this breakdown helpful, don't forget to like, subscribe, and stay curious because there's always more to explore in the world of AI. See you in the next one.